Howdy, we are group 624. Without further ado, let me introduce our project. It is about data augmentation for handwriting letter recognition. We all know what sketch recognition is, but the motivation that drive us to work on this project is that sketch recognition remains a significant challenge due to the limited training data for some languages and the substantial intra-class variance of freehand sketches, or jitters, for the same object. So our work is actually trying to provide a proof of concept that with a small amount of data, we can achieve a result roughly the same as a model trained using a large amount of data. We currently work on a subset of a cargo dataset, and if it turns out it is a success, then this method can be extended to more languages with small amount of data. And we use data augmentation, which take advantage of Bezier pivot-based deformation to expand data. And the dataset we pick contains 10 numbers, 52 letters, uppercase and lowercase, 26 for each. And add them up, we get 62 different classes in total. Each class contains 55 different sample images. So in total, we have 62 different classes times 55 sample images. And then we get 3,410 images in this data set. This is our control group. From this data set, for each class of 62, we pick 5 sample image randomly. For each sample image of the 5 chosen ones, we generate another 10 sample images. Therefore, we get 62 different classes times 5 chosen sample image from each class times 10 new generated samples plus 1 original chosen image sample, and then we get 3,410 images as well. This is our test group. And the way we generate 10 new images is first we skeletonize each image to get points on each line segment, and then we break all connection between line segments so that each line has only 2 endpoints, and then we apply Bezier-based deformation onto each line segment 10 times to get 10 new versions of original image. Once we get these 10 new images, we delete them or thicken them. This is the general idea of implementation, and then save them in a folder. And after getting these 2 groups of 3,410 images, we run ResNet 152 as our model to train the data. First we load images and resize them. We resize them into the same X and Y dimension, and then label each image with their file names. And then encode the label with 1 hot encoding. And this is the part of making labels. And then we split the images so that 80% for training and 20% for testing. Then we load the ResNet 152 model. Set epoch to 100, learning rate 0.02, batch size equal to 16. Then transform the data into tensor. And then this we make a data type to combine each label and image together for both test and train data. And this is our model. 2048 is the and this is the we loaded, and then this is full connected. 2048 is the output dimension, and 62 classes in total. And we use cross entropy loss to define the loss, and this is the optimization method. And this train loss is used in training, and value lot is for testing, and accuracy is for each epoch. And evaluate is to get the accuracy, and the trend for training. And this is to print out the result and how we execute our evaluation plan. For each epoch of 100, we set start time and use train function to train model, and then we get train loss and put it into the list. And we call evaluate based on the current weight, and then we load the data from test loader into the train model to evaluate and get an output. And then we print the best accuracy from the 100 epoch and print it out. And as you can see, the accuracy below it is the result. Epoch 1, epoch 2, epoch 3, 4. And as you can see, the accuracy keeps increasing from epoch 1 all the way up. And to the bottom, we get this this best accuracy, which is 89%. We fed original dataset and data augmented dataset into this code. For original dataset, the accuracy was 86%. For the data augmented dataset, the accuracy, as you can see, is 89%, which is higher. So the proof of concept our project is trying to provide can be deemed a success.